Hey guys, okay, so what we're going to do in this presentation, it's topic 6, we're going to do some examples involving momentum and energy. So right here on the first slide, I've just summarized the important equations. Here's a little picture showing a particle of rest mass m0 traveling with some speed u. You can find these in the last presentation, and also don't forget to look at the summary notes. You'll find these equations summarized there. Okay, now before we do the examples, a word about units. That's on the next slide. SI units, mass, kilogram, momentum, kilogram meter per second, energy, joule. They're humongous when we're talking about these small particles. Again, the only time we're really going to have to use relativistic mechanics is when we have these tiny particles flying around, and their energies are nowhere on the joule scale. So there are common, what I'm going to call relativistic units that are used based on the energy unit, the mega electron volt. So right here, the mega electron volt, 10 to the 6 electron volts, you're going to hear me call that MeV. All right, so if you hear MeV, that means mega electron volts. That's what people just say MeV instead of capital MEV. All right, now, the way we do this is, if you look, for instance, right here at relativistic mass, right? So, I'm sorry, rest energy, not relativistic mass. Energy is a mass times speed of light squared. So dimensionally, a mass can be expressed as an energy per c squared. So instead of using the kilogram, what we're going to do is we're going to express our mass in MeV per c squared. Okay, so for instance, if you look over here in table 6.2, we have the rest masses of some common particles. The electron, 9.11 times 10 to the minus 31 kilograms. You can express that as 0.511 mega electron volt per c squared. So in other words, if I take 9.11 times 10 to the minus 31 kilograms, multiply it by 3 times 10 to the 8 meters per second, quantity squared, that's c squared, I'm going to get so many joules. If I convert that joules, right, the number of joules into mega electron volts, I would get 0.511. Okay? All right, so energy, MeV, mass, MeV per c squared, and then momentum, what we do is we remember for a photon, the momentum is energy per c, right, divided by c. So any momentum can be expressed as an energy per c. So instead of using kilogram meter per second, we're going to say so many MeV per c. You'll see how that works in the next example on the next slide. So let's go to that. So this example, I'm going to go presentation mode so we can look at each line as we do it. So we're just going to find the momentum, the kinetic energy, and total energy of an electron moving at half the speed of light. Okay, so the first thing, the momentum. Now, first thing, guys, if you're given a speed, find the gamma factor. The gamma factor and the speed, they're linked together. So I'm going to find the gamma factor for 0.5 c. Here's the key when you're doing these relativistic calculations. Never put in the value of c unless you have to go and find something in SI units. Leave the speed as a fraction or a decimal times c, because what happens in the gamma factor, right? If I put in 0.5 c here for u, the c squareds are going to cancel, and I'm just going to be left with 1 minus 0.5 squared square root in the denominator. So it's a lot easier when you're punching these numbers in your calculator. We get a number of 1.155 for the gamma. Now that we have the gamma, we use the definition of the momentum. And watch. See this m naught right here? Don't put in kilograms, put in, since it's an electron, 0.511 MeV per c squared. If we put u as 0.5 c, look, c over c squared, I've automatically have a c in my denominator. So all I have to do on my calculator is punch in 1.155 times 0.511 times 0.5. I've got 0.285, and my units are going to be mega electron volts, MeV per c. Now, if your instructor says, well, I would like that in SI units, because your instructor is I don't know, he's just like that, right? You can do it. It's a little bit more to punch in your calculator, though. What you would have to do is actually divide by the value of C, 3 times 10 to the 8 meters per second, convert this mega electron volts to joules. So to do that, I did two steps. I said, okay, there's 1 million electron volts in 1 mega electron volt. Then there's 1.6 times 10 to the minus 19 joules per electron volt. And I end up with 1.52 times 10 to the minus 22 kilogram meter per second. Okay? But again, you're only going to have to do that if you're instructed to do so. Okay, let's find kinetic energy. All right, using the definition, it's gamma minus 1 times m naught c squared. So we have our value of gamma up there. And watch, m naught, we just, again, put in the rest mass in MeV per c squared. And then since we have to multiply by this c squared, boom, boom, the c squareds just cancel. And I'm left with just a number to put in my calculator of 0.155 times 0.511, and I automatically have MeV. If you have to do the conversion, you can do it and get that number of joules. And then total energy, that's just the sum of kinetic and rest energy. So we add those two, right? And we get a total energy of 0.5902 MeV. Okay? So that's the nice thing about using these common relativistic units in these equations. Okay. Oh, yeah, and I guess if asked, you can convert that, again, to joules. Okay, let's do another example. This is something that you guys should be able to do, for instance, on test 4, when I give it to you. An electron is moving at half the speed of light. How much more energy, right? Or I should say, how much energy is needed to increase its speed to 0.9 c? So we want to speed this up from half the speed of light to 90% the speed of light. And then the next question is, well, then how much more energy would you need to go from 90% the speed of light to 99? And then how much energy would you need for the electron to reach the speed of light? These are really all the same type of question. And whenever you're asked, how much energy does it take to go from this speed to this speed? That's really just the change in the kinetic energy. So find the difference in the kinetic energies. So the initial speed, there's an initial kinetic energy. The final speed, there's a final. But if we actually put in the formulas first without putting in the values, we get a nice simpler expression. It turns out that that delta K is just the difference of the two gammas times the rest energy. So for instance, let's do A. Our initial speed is half the speed of light. Our final speed is 0.9. We calculate the two gamma factors. We then subtract them, right? And then just multiply by m naught c squared. But again, m naught is 0.511 MeV per c squared, multiplied by the c squareds. The c squareds go away, and we're left with 0.582 MeV. Okay? Now, what about if we just want to go a little bit faster? So we're now at 0.9 c, and we just want to go up to 0.99 c. Well, you might see where this is going. Because of how the gamma factor increases dramatically as the speed is approaching the speed of light, it turns out that the difference between the two gamma factors, and we're doing this problem just like we did A, is greater than it was in A. And look, you need 2.45 MeV now to go from 90 to 99%, when 0.582 MeV got you all the way from 50 to 90% the speed of light. All right? So to go faster and faster and faster, it takes more and more and more energy. In fact, the answer to C is what? What if we actually put the speed, the final speed, at 1 speed of light? Well, it turns out the gamma factor goes to infinity. So it would take an infinite amount of energy, and that is impossible. So it is impossible for any particle with a rest mass to reach the speed of light. A photon with no rest mass is already traveling at the speed of light. That's a neat result. All right, there's one more example I want to look at, and this is something we haven't talked about yet. And it's an example of what we call matter and energy equivalence. It has a cool name. It's called Annihilation, and this actually does happen in our universe. So you may have heard of antimatter. Antiparticles are still made out of what we would call regular old matter. Okay, the term antimatter is sort of a strange term because you think it's something that's not matter. It is matter, but these antiparticles are not real common because whenever they meet their particle counterpart, they will completely convert to a 2-photon gamma burst. So you get matter converting to pure energy. An antiparticle is a particle that has the same rest mass as its particle counterpart, but opposite charge. So for instance, the electron, there is in our universe what we would call an anti-electron. A more common name for that is the positron, which you may have heard. The positron has the same rest mass as the electron, but positive charge, positive 1.6 times 10 to the minus 19 coulombs. Okay, but again, we don't see a lot of positrons because whenever they run into an electron, boom, they disappear and 2 photons appear. It's quite remarkable. All right, so look, you should be able to analyze a pair annihilation where the 2 particles start at rest. So for instance, as you see in this picture, suppose we have a particle and its antiparticle just sitting there, and they're going to annihilate one another. They both have rest mass m naught. Right after they annihilate, we're going to get 2 photons. Now, because momentum has to be conserved and energy has to be conserved, before this process occurs, there's no momentum because we're considering them at rest. So the 2 photons, they have to have the same size momentum and they have to travel in opposite directions. So when we add the vector momentums, we get 0. Now, because the energy, total energy available to these photons is twice the rest energy of one of the particles, because they have to have equal momentum, they're going to have equal energy. So each of these photons has 1 rest energy. Right, so we can write that the energy of a single photon is just going to be the rest energy of one of the particles, m naught c squared. But then if we remember that a photon wavelength is that 1243 eV nanometer over the energy of the photon, we just put in m naught c squared there. All right, so for instance, speaking of the electron and the positron, what if we put in the rest energy of those guys, right? The rest energy is 0.511 MeV. So now remember, this is a million, this is a mega. Up here, that's just a regular old electron volt, this is a mega. So if you punch that in your calculator, you're going to get 2.4 times 10 to the minus 3 nanometers, or we could call that 2.4 picometers. That would be the wavelength of each of these guys, okay? All right, so there's another neat example using these relativistic expressions. Okay, that's it. All right, see you next time.